Electrical engineering is built upon a foundation of fundamental concepts and principles. A crucial aspect is understanding circuits, which are pathways for electrical current to flow. These circuits consist of various components, each playing a specific role. One of the most fundamental laws governing electrical circuits is Ohm's law, which establishes the relationship between voltage, current, and resistance. Voltage, measured in volts, is the electrical potential difference that drives current through a circuit. Current, measured in amps, is the rate of flow of electric charge. Resistance, measured in ohms, is the opposition to the flow of current. Ohm's law states that voltage equals current multiplied by resistance. In mathematical terms, voltage equals current times resistance. This simple equation is the cornerstone of circuit analysis. Another critical set of laws is Kirchhoff's laws, which provide a framework for analyzing complex circuits. Kirchhoff's current law, also known as Kirchhoff's first law, states that the total current entering a junction or node in a circuit must equal the total current leaving that junction. This law reflects the conservation of charge. In other words, what flows in must flow out. Kirchhoff's voltage law, also known as Kirchhoff's second law, states that the sum of the voltage drops around any closed loop in a circuit must equal zero. This law reflects the conservation of energy. The voltage gain must equal the voltage drops in a closed loop. These laws allow electrical engineers to systematically analyze and solve complex circuits with multiple components and loops. Power is another essential concept in electrical engineering. Electrical power, measured in watts, is the rate at which electrical energy is transferred or consumed. Power is calculated as the product of voltage and current. In mathematical terms, power equals voltage times current. Understanding power is crucial for designing efficient and safe electrical systems. Electrical components are the building blocks of circuits. Resistors, as mentioned earlier, oppose the flow of current. Capacitors store electrical energy in an electric field. Inductors store electrical energy in a magnetic field. Diodes allow current to flow in one direction only. Transistors act as electronic switches or amplifiers. Integrated circuits, or chips, contain a large number of interconnected transistors and other components, forming complex electronic systems. Understanding the characteristics and behavior of these components is essential for designing and building electrical circuits and systems. The analysis of alternating current, or AC, circuits introduces new considerations. In AC circuits, the voltage and current vary sinusoidally with time. The frequency of the AC signal, measured in hertz, is the number of cycles per second. Reactance is the opposition to the flow of current in an AC circuit due to capacitance and inductance. Impedance is the total opposition to the flow of current in an AC circuit, including both resistance and reactance. Power factor is a measure of the efficiency of power transfer in an AC circuit. Understanding these concepts is crucial for designing and analyzing AC power systems. Electrical safety is of paramount importance in electrical engineering. Electrical shock can be a serious hazard. Proper grounding is essential for preventing electrical shock. Overcurrent protection devices, such as fuses and circuit breakers, protect circuits from excessive current. Insulation prevents electrical current from flowing where it is not intended to. Adhering to electrical codes and standards is crucial for ensuring safety in electrical installations. The National Electrical Code, or NEC, provides comprehensive guidelines for safe electrical practices. Grounding is the process of connecting electrical equipment to the earth, providing a low resistance path for fault currents. This helps to prevent electrical shock and damage to equipment. Overcurrent protection devices, such as fuses and circuit breakers, are designed to interrupt the flow of current when it exceeds a safe level. Fuses contain a metal element that melts and breaks the circuit when the current is too high. Circuit breakers use a mechanical mechanism to trip and interrupt the circuit. Insulation is a non-conductive material that prevents electrical current from flowing between conductors or to ground. Proper insulation is essential for preventing electrical shock and short circuits. Electrical codes and standards are developed to ensure the safety and reliability of electrical installations. These codes and standards cover a wide range of topics, including wiring methods, grounding, overcurrent protection, and equipment installation. Adhering to these codes and standards is crucial for protecting people and property from electrical hazards. Digital electronics is a branch of electrical engineering that deals with digital signals and circuits. Digital signals are discrete signals that can have only a finite number of values, typically 0 or 1. Digital circuits use logic gates to perform logical operations on digital signals. Logic gates include AND gates, OR gates, NOT gates, NAND gates, NOR gates, XOR gates, and XNOR gates. These gates can be combined to create more complex digital circuits. Microprocessors are integrated circuits that contain the central processing unit, or CPU, memory, and input/output, or I/O interfaces. Microcontrollers are similar to microprocessors but are typically designed for embedded applications. Digital signal processing, or DSP, is the processing of digital signals using algorithms and techniques to extract information or modify the signals. Understanding digital electronics is essential for designing and building digital systems. Signal processing is a fundamental aspect of electrical engineering that involves manipulating and analyzing signals to extract information, enhance quality, or modify content. Signals can be analog, continuous in time and amplitude, or digital, discrete in time and amplitude. Common signal processing techniques include filtering, which selectively attenuates or amplifies certain frequency components of a signal, and transforms, which converts signals from one domain to another, such as the time domain to the frequency domain using Fourier transforms. Modulation is the process of encoding information onto a carrier signal for transmission over a communication channel. Demodulation is the process of extracting the information from the modulated carrier signal at the receiver. Signal processing is used in a wide range of applications, including audio and video processing, communications, and control systems. Control systems are used to automatically regulate and maintain a desired output or behavior in a system. Control systems consist of sensors, which measure the output of the system, controllers, which compare the measured output to the desired output and generate a control signal, and actuators, which implement the control signal to adjust the system. Feedback control systems use the output of the system to adjust the control signal, providing improved accuracy and stability. Control systems are used in a wide range of applications, including robotics, aerospace, and industrial automation. Communication systems are used to transmit information from one location to another. Communication systems consist of a transmitter, which encodes and transmits the information, a channel, which is the medium through which the information is transmitted, and a receiver, which receives and decodes the information. Modulation techniques are used to encode the information onto a carrier signal for transmission. Common modulation techniques include amplitude modulation, or AM, frequency modulation, or FM, and phase modulation, or PM. Communication systems can be wired or wireless. Wireless communication systems use radio waves to transmit information. Understanding communication systems is essential for designing and building communication networks. Electromagnetic fields are a fundamental aspect of electrical engineering. Electric fields are created by electric charges. Magnetic fields are created by moving electric charges or electric currents. Electromagnetic waves are created by accelerating electric charges. Electromagnetic waves propagate through space at the speed of light. The electromagnetic spectrum includes radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays, and gamma rays. Understanding electromagnetic fields is essential for designing and building antennas, waveguides, and other electromagnetic devices. Power electronics is a branch of electrical engineering that deals with the conversion and control of electrical power. Our electronic devices, such as diodes, transistors, and thyristors, are used to switch and control electrical power. Power electronic circuits are used in a wide range of applications, including power supplies, motor drives, and renewable energy systems. Power electronic converters are used to convert electrical power from one form to another, such as alternating current to direct current or direct current to alternating current. Understanding power electronics is essential for designing and building efficient and reliable power systems. Renewable energy systems are becoming increasingly important as the world transitions to a more sustainable energy future. Renewable energy sources include solar, wind, hydro, geothermal, and biomass. Solar energy systems convert sunlight into electricity using photovoltaic cells. Wind energy systems convert wind energy into electricity using wind turbines. Hydro energy systems convert the energy of flowing water into electricity using hydroelectric dams. Geothermal energy systems extract heat from the Earth's interior to generate electricity. Biomass energy systems burn organic matter to generate electricity. Understanding renewable energy systems is essential for designing and building sustainable energy solutions. In conclusion, electrical engineering encompasses a vast array of concepts, principles, and applications. A solid understanding of these fundamentals is crucial for anyone pursuing a career in electrical engineering or related fields. These fundamentals are foundational and should be remembered in any electrical concept to give a broad overall understanding.